Good afternoon, my name's John Johnston and welcome to our webinar on condensation in the roof space. If you have any questions, feel free to type them into the comment box as we go along, or email them to webinar@proctorgroup.com and we'll review them in the question and answer session at the end. In this presentation we're going to take a look at condensation, what it is and what causes it, along with some of the design considerations and regulations involved. We'll also take a look at the types of vapour permeable underlays available and some of the differences in the performance between them. So what is condensation? Condensation is the formation of liquid water when warm humid air comes into contact with cold surfaces. The warmer the air in an environment is, the more water vapour it can retain. However, when this moisture-laden air cools down, its capacity to retain water vapour reduces and the water vapour will turn back into liquid. The most common example of this is the bathroom mirrors, where the warm air in the bathroom can support a lot of moisture. For example, a shower, but when it hits the cold surface of the mirror, it loses this ability, causing the mirror to fog up. As well as showers and bathing, there's a number of other moisture sources present in buildings. Cooking can produce a fair amount of water vapour, not only through the obvious sources of water boiling in a pan, but also the byproduct of the combustion of certain gases. Cooking can also raise the temperature of a room, which in turn can increase the humidity of the air. Laundry is also a significant moisture source, both from steam irons and drying out of clothes. Clothes being hung over radiators to dry out is one of the most common causes of condensation and damp problems in housing. Finally, the building occupants themselves produce a lot of moisture through breathing and sweating. Even while sleeping, this represents a substantial source of moisture, and activities such as sport produce significantly higher moisture loads. When considering condensation control strategies, the activities taking place in the building are among the most important factors. Another common example of condensation is cold drinks can on a warm day, but how and where does condensation occur in the context of buildings? In the habitable areas of buildings, warm, humid internal air creates what's known as vapour pressure. Vapour pressure is the driving force behind condensation risks in buildings. In the UK, this process works from inside to outside, pushing the moisture into the walls, floor and roof of a building, towards typically cooler and less humid conditions outside. So how does this vapour pressure give rise to a condensation risk? The insulation in the building fabric helps keep the indoor temperature more or less constant. But as we move outward through the building element, the temperature will drop sharply across the insulation layer. As the temperature drops, the air loses its ability to retain water vapour. At a certain temperature, the air will become saturated and lose its ability to contain the water vapour. This temperature is known as the Dewpoint Temperature, and is a product of vapour pressure at a given point in the structure, as well as the vapour resistance of the individual layers in the construction. Provided the actual temperature remains above the Dewpoint temperature, there will be no significant risk of condensation occurring. If the actual temperature drops low enough to coincide with the dew point, the air will become saturated and the condensation will occur at the point the temperatures meet. The nature and severity of the condensation problems will be determined by the extent to which the temperature drops below the dew point and where in the structure this occurs. If the wall is cold and poorly insulated, the dew point will occur on the internal surface, which causes surface condensation. This is fairly common in bathrooms and kitchens, particularly in older properties which may have solid brick or stone walls. If the meeting point is within the fabric of the building element, this produces what is called interstitial condensation. This is most obvious in lofts with poor ventilation or low-spec vapour permeable underlays, but it can also be hidden completely within the element. It's therefore important that designers ensure this does not occur, as it may be invisible to the occupants. It is also possible to have reverse condensation, which occurs where the indoor conditions are cooler and less humid than the outside conditions, in which case the normal vapour drive is reversed. It's very rare that this occurs in climates like the UK. However, in buildings such as ice rinks and cold stores, this should be taken into consideration. So now we've discussed what condensation is and how it occurs, let's take a look at some of the problems it can cause. If condensation leads to persistent damp in a specific area, it can cause damage to the internal finishes. This damage can range from discoloration and growth of mould spores. Mould spores within the habitable space of a building can give rise to serious health problems for the building occupants, particularly children and the elderly or anyone with respiratory problems. Damp spots and any subsequent mould can be an indicator of cold spots, such as at junctions, corners or areas where there is substantial cold bridging. Surface mould can also be an indicator of poor airflow, such as behind furniture, at the back of built-in wardrobes or in specific areas in attic spaces. Some insulation materials, particularly fibrous types like glass wool, will absorb the moisture arising from interstitial condensation, and since the water conducts heat better than air, this will reduce the insulation's performance. If the dampness is caused by locally reduced temperatures such as a cold bridge or air leak, this decrease in insulation performance will increase the rate at which the condensation will form, resulting in a vicious circle of degrading performance. In most cases, timber will begin to rot if the moisture content is above 20% for longer than 60 days. Rotten structural timbers will severely reduce the lifespan of a building, so it's critically important to ensure moisture is managed to avoid this. It's also important to remember that as timber absorbs moisture, it may well swell and distort due to expansion. The converse is also true. If the timber gets wet and swells during construction, it may subsequently shrink as it dries, which can also lead to problems. Although metal elements are generally more resistant to moisture damage than timber, they are not immune. The corrosion of metal work can weaken structures. Corrosion damage to metal elements like roofing sheets can also lead to further moisture problems due to water ingress in adverse weather. Water ingress into electrical services and network cabling will also have obvious negative effects, but it's also worth considering that any structural distortion due to swelling timber or corroded steel can also affect building services by overstressing cables, pipes and conduits. There are two principal issues associated with items stored in lofts. Firstly, damp conditions can lead to damage due to mould growth or rot. Secondly, items in boxes can block roof ventilation or obstruct airflow, which can lead to problems in otherwise well-designed and constructed roofs. We'll now take a look at some of the factors affecting pitched roof design and how we can design out condensation problems from the start. The building fabric, typical weather conditions and anticipated occupancy patterns and uses will all interact to define the moisture risk associated with the construction. These ground rules must be identified and understood to form the basis of a good hygrothermal design strategy. Once an understanding of the building, weather and occupancy is achieved, the designer can then focus on ensuring the heat, air and moisture movement within the structure is properly balanced. Ensuring a healthy environment for the building's occupants and a long life for the building is the foundation of HAM principles in building design. While that might seem simple enough, in reality this balance of heat, air and moisture is influenced by a great many factors depending on the precise nature of the project and its requirements. We'll now take a look at some of these factors in greater detail. In refurbishment projects, there may be pre-existing condensation issues to resolve, particularly related to convection tightness and cold bridging. Older structures were not usually designed or built with much thought given to these issues, so it might not be that straightforward to resolve these problems, either in practice or economically. The building may also have been modified or upgraded over its lifespan, and additions such as double glazing, blocking up chimneys and ceiling drafts may have created condensation issues which did not exist before. Modern materials may also have very different hygrothermal properties to those they replace, such as gypsum plasterboard compared to traditional lime plaster. This might require special treatment in order to avoid problems, necessitate sourcing unusual materials or scales. On paper, new build presents far less problems. However, designers have to bear the practicality of installation and site conditions in mind when detailing condensation control measures. It's easy to draw a detail which is completely unachievable in reality, even assuming the contractors are sufficiently skilled and aware of the importance of vapour control. It's also important to schedule work in order to minimise damage following trades might cause to the vapour control measures. This avoids plumbing and electrical services being run through membranes which are supposed to provide a vapour or airtight seal. Providing service voids within the sealed envelope goes a long way to preventing these problems. Finally, construction moisture must be considered, and wet trades like screeding and plastering will introduce additional moisture loading which may not have been accounted for. Timber frame buildings are typically built under drier off-site conditions, which not only reduces initial moisture loads, but means a wind and watertight envelope can be achieved in less time. Tighter tolerances and better quality control also help reduce problems, but this might mean that the building is less able to tolerate issues arising from poor installation or damage to prefabricated elements that might occur. Traditional masonry buildings will have higher moisture loading from wet trades and less precise construction process that places greater emphasis on good workmanship on site. They do, however, have better fabric heat storage characteristics, which can help stabilise temperature swings, and the inherently leakier and more permeable construction can reduce the risks associated with trapping moisture, provided this permeability is properly accounted for in the design process. The use of sarking materials such as plywood or OSB or traditional softwood planks will have a big impact on the way moisture flows through a loft. Some underlay membranes certification may impose additional requirements or restrictions on its use. Traditional roofing practice such as Scottish method of slating directly into sarking boards with no battens will be different again, and any membrane specified for this application should have full certification for such applications. It's not only traditional slating that will affect condensation in lofts. Even using a standard tiled roof, the air openness of the outer cover must be accounted for, and if the tiles are particularly airtight or if a metal roof covering is specified, additional venting of the batten cavity may be needed. BS 5250 and BS 5534, both of which we'll discuss shortly, outline when coverings can be considered air open, what measures must be taken if they're not, and what effect wind uplift will have both on the outer covering and the roof underlay. Finally, the physical layout of the roof has to be accounted for, and particularly complicated roofs might pose problems when it comes to ensuring all areas are adequately ventilated and there are not dead spots where the moisture-laden air can accumulate and condense. Subdivisions of roof areas, for example for fire compartmentalisation, can further exacerbate this issue, as can specific architectural detailing of the overall aesthetic, which may preclude adding additional ventilation. BS 5250 details specific requirements for ventilating roofs and controlling condensation, and we'll move on to discuss that now. BS 5250 is the Code of Practice for Condensation Control and is referred to by the UK building regulations, which do not address the specifics of condensation control directly. BS 5250 gives specific detailed guidelines on how to ventilate all types of roof, but it does not address the non-ventilated roof construction, instead referring the designer to specific third-party guidance if ventilation is to be omitted. This is typically a BBA certificate, although any relevant and equivalent European technical approval document can be used. As well as outlining ventilation requirements, BS 5250 defines performance criteria for types of roofing underlay. These are HR underlays, traditionally non-permeable underlays such as bitumen felt, with a vapour resistance greater than or equal to 0.25 meganewtons second per gram, and LR underlays, which are modern breathable felts with a vapour resistance less than 0.25 meganewtons second per gram. HR underlays will always require the use of ventilation, while LR underlays can be used without ventilation provided third-party certification is available and its conditions are adhered to. BS 5250 also recognises the benefit of air permeable membranes with regards to condensation control, but does not define any performance criteria in this area, again leaving the specifics to third parties. For HR type underlays, ventilation openings are typically required at the eaves and or ridge of the roof to ensure sufficient airflow is provided to remove moisture vapour from the loft space. These requirements are detailed in Table H2 of BS 5250. However, we believe a simpler and more universally applicable solution is to omit the ventilation layer altogether by using a vapour permeable type LR underlay. When using an LR underlay, the vapour can escape through the entire roof surface driven by the internal vapour pressure. In theory at least, that means air movement through ventilation is not required. However, as we've discussed, BS 5250 does not directly address non-ventilated roofing, and membranes used without ventilation must therefore be covered by third-party accreditation such as BBA, BM Trada, etc. Conditions for use of such membranes are given in these certificates rather than BS standards, and if ventilation is omitted, these conditions must be adhered to. However, it's not always quite that simple, as we shall see shortly. A great many membranes meet the LR spec from BS 5250. However, within this, there can be significant performance variations. In addition to being vapor permeable, LR membranes can either be airtight or air open. As is noted in BS 5250, air open membranes have certain advantages as regards reducing condensation risks. Here we can see 3 different LR membranes installed on the same roof. While there is a lot in common, the specific product certification for each membrane will have subtle differences. So while all are broadly suitable for this application, the specific detailing required and the overall performance may vary considerably. Product certificates and technical guidance documents go into a lot of detail about these specifics, and these may include requirements to use vapour control layers at ceiling level or to specify insulation with reduced vapour permeability. Features such as sarking boards or dormer windows may not be covered by the product certification or may impose additional requirements. Even apparently simple things such as the amount of drape required in counterbattens are needed can vary between membranes. This variation means that it's important to have a good appreciation of all the different membrane types that are available, so let's now take a look at some of these in more detail. Flash spun HDPE membranes are typically 2-layer products and are vapour permeable while being air and watertight. In general, the vapour permeability for these types of membranes is at the lower end, but they can provide an effective air barrier which can theoretically improve energy efficiency in applications where they can be specified with no ventilation, but they will require the use of either a vapour control layer or a well-sealed ceiling. We'll be discussing the implications of membrane air tightness in more detail shortly. Phelim laminate vapour permeable membranes are typically composed of 2 layers of polypropylene with a Phelim core. Most of the vapour permeability and the water holdout performance is governed by the Phelim layer. However, it's quite fragile, so the outer layers serve primarily to protect the core from damage. Phelim laminate membranes are typically airtight and are similar to flash spun membranes in terms of vapour permeability. They do tend to have a slightly higher water holdout performance. However, all membranes used in roofing application should meet the relevant W1 waterproofing standard. As with all airtight membranes, Phelim laminates depend purely on the vapour drive to transport moisture out of the roof, so they may be less able to cope with excess moisture loads and as such may require the use of a vapour control layer or additional ventilation. Phelim laminates are the most common type of vapour permeable underlay, and it's also worth noting that a lot of Phelim laminate membranes are rebrandings of the same base material. Examining the details in the product certification will reveal if this is the case. Polypropylene membranes with a melt-blown core, such as our roof shield, replace the microperforated Phelim core with a layer of microporous fibres. This comprises a matrix of fibres many times smaller than the human hair, which allows the smaller water vapour molecules to pass through, while larger water molecules are blocked. Membranes with a melt-blown layer offer a higher permeability to water vapour, further boosted by air permeability, which provides actual air changes through the loft space. This comes at the expense of a slightly reduced waterhead compared to other membrane types. However, as the membrane still meets the requirement specification for W1 water tightness standard, this is of little importance. Because the membrane is also air permeable, excess moisture loadings are easily accommodated, greatly reducing condensation risks and meaning there are few restrictions of the use of such membranes. Vapour control layers and additional ventilation are typically not required for common roof constructions. We'll now take a look at the implications and benefits of air permeable roofing underlays. In 2012, the NHBC released this guidance document in response to the complaints for homeowners regarding condensation issues. These complaints noted condensation appearing over winter months shortly after completion, while the excess construction moisture from the screening and plastering is still drying out. This is generally discovered by homeowners unpacking their Christmas decorations. To remedy this problem, the NHBC mandated that roofs with low resistance type LR underlays should be fitted with an additional 5 mm of ventilation openings at ridge only. In theory, this open ridge boosts vapour transfer during the drying out period after completion. In practice though, the airflow out the ventilated ridge is inhibited by the lack of air inlets, so it's not clear if this approach makes a big difference to the condensation risks. In addition to the 5mm ridge ventilation, the ceiling must also be well sealed as defined in BS 9250. Aside from obvious requirements like not having any gaps or cracks in the ceiling, this standard sets air leakage requirements for hatches and downlighters and requires sealing of service penetrations using suitable proprietary products, all of which can complicate the design and construction process and potentially introduce unforeseen costs and delays. Another concern here is that by introducing a 5mm gap at the ridge, there is an additional pathway for water ingress, both during construction and in the event of damage to the primary roof covering. This means that the roof cannot be considered watertight until the roof covering is completed, delaying works or internal finishes and services that could otherwise be started. Finally, this gap means that the roof is not airtight, negating the energy performance benefits used as a selling point by the airtight underlay manufacturers. It also places a lot of emphasis on the quality of the ceiling installation, which can be an issue if electricians, plumbers, ventilation installers, etc. are not aware of the specific requirements of BS 9250. So given these issues with the NHBC guidance, is there a way we can avoid this? The same NHBC document includes an exemption to these rules. However, this is not referenced in the main NHBC standards documents, so it may not be immediately apparent. The way around adding the ridge ventilation is to use an air permeable membrane carrying appropriate certification. This allows the use of completely unventilated roof constructions. Our roof shield membrane is BBA certified as air permeable and therefore qualifies under this exemption and can be used without ventilation or vapour controlled as detailed in section 7 of the certificate. For the avoidance of doubt, we have written clarification from the NHBC that this is the case. There is a sound basis for this difference between airtight and air permeable membranes, and testing to back it up was conducted in the early 2000s at BRE Scotland. The Partners in Innovation PII project Improved Thermal and Moisture Performance of Pitched Roofs was undertaken by the BRE and Caledonian University and completed in 2004. The aim was to test and model the performance of different types of LR underlays and compare these results to conventionally ventilated roofing. A variety of test rigs were used to simulate conditions in a variety of roofs. The 4 test cases were shown here, and prior to testing all 4 test rigs were pressurised to determine the equivalent ventilation openings that would be necessary to replicate the air leakage characteristics of an unventilated roof. Here we're going to focus on the worst case result from tests where the condensation risk was elevated as high as possible. In the worst case test, not only were the loft hatches unsealed, but they were left open, and the moisture load increased by heating water baths to simulate an open hatch in a humid bathroom environment. The combined effect on this is to raise the temperature and the vapour pressure in the loft, making it more likely that condensation problems will occur. During the extreme test period, heavy condensation was noted on the underside of both the airtight LR underlay and the traditional roofing felt, while the air permeable underlay on the first pair of roofs was free of moisture. In these roofs, the air permeable underlay allows airflow through the loft, so as well as the vapour drive pushing moisture from inside to out, there are actual air changes taking place. This not only increases the ability of the roof system to transport moisture vapour safely out of the building, but it makes it harder for condensation droplets to form on the roof underlay. It is because of this testing that both BS 5250 and the NHBC recognise that air permeability of roofing underlays plays a significant role in reducing condensation risks in pitched roofing. As well as condensation control, an important factor in roof design and underlay specification is the effect of wind uplift forces on the roof system, and this is covered by the Code of Practice for Slating and Tiling, BS 5534. As wind blows over the roof structure, the airflow presses on the windward side, creating a downward force, the wind pressure. On the leeward side of the roof, the airflow reduces the pressure, creating a suction which pulls the roof upwards. This is the wind uplift force. These two forces act on the entire roof system, and the starting points of this chain of forces are the outer covering and the underlay membrane. The resistance of the uplift force is shared between the outer covering and the underlay depending on the air openness of both parts. It follows therefore that wind uplift forces will have a greater effect on airtight systems than air permeable ones, as airtight systems will resist the flow of air by their very nature. If the roof is not correctly designed to resist wind uplift forces, then in extreme cases the tiles and slates or outer covering can be damaged. This damage will be mainly caused by uplift forces directly removing the slates or tiles by sucking them up and off the roof. In theory, it could also occur due to the underlay membrane ballooning and pushing them off, although there is little, if any, conclusive evidence of this occurring. The BS 5534 sets criteria for underlays to resist wind forces and divides the UK into 5 wind zones. This table gives the uplift resistance force for the roof shield membrane for each installation configuration, along with the measures that must be taken when used in a given wind zone. As we can see here, in zones 1 to 3, no special measures are required at 345mm batten spacing centres. However, in a more extreme conditions of zones 4 and 5, designers will either need to reduce their batten spacing to 250mm, fit counter battens or tape joints. If, however, they're using traditional Scottish slates into softwood sarking, then use is unrestricted in all zones. So how do we determine this uplift resistance? This is the BRE's wind uplift testing facility, where underlay samples are tested to determine their performance in resisting uplift forces and the effect those forces have. Samples are fixed into a test frame and the space below, known as the plenum, is pressurised. As can be seen here, the underlay in this case is a roofing felt. It will balloon upwards under this pressure. The maximum pressure that can be resisted is determined by the point at which the membrane reaches 35mm above rafter level or is unable to sustain further pressure increases. Here we can see the roof shield air permeable underlay on the test rig. Although air permeable membranes will balloon eventually, it takes a higher pressure to achieve this result, as a proportion of air will flow through the membrane instead of deflecting it. BS 5534 also contains definitions on membrane types and also specifically defines for the first time what performance is required for an air permeable membrane. Under the definition given in BS 5534, an air open permeable underlay must have a vapour resistance not more than 0.25 meganewtons per second per gram and an air permeability of not less than 20 metre cube per square metre per hour. This removes any uncertainty about whether or not an underlay can be treated as air permeable, but does not, however, address any effect of increasing or decreasing air permeability. BS 5534 also introduces new definitions on types of ceiling and addresses the influence of the ceiling on the performance of the roof as a whole. This first type of ceiling, a continuous ceiling, is analogous to the well-sealed ceiling defined in BS 9250. However, the definition is less prescriptive, simply stating a permeability that must be achieved. Ceilings failing to meet this criteria are classed as discontinuous. Discontinuous ceilings are not classed as well sealed as regards to wind uplift zoning and can limit the suitability of a given underlay membrane for site conditions. We will now move on to discuss a new alternative methodology for air permeable testing, pulse air testing. In this testing, a high pressure pulse of air was used to determine the comparative performance of an unventilated roof fitted with roof shield underlay against an otherwise identical roof fitted with an airtight underlay and ridge only ventilation. The testing was conducted on both semi-detached and detached properties, and in this test the decay time of the pulse of high pressure air is measured, and this is used to determine the overall air permeability of the roof. In both cases, roof shield roofs are fully closed with no openings provided at either eaves or ridge, so moisture vapour may only escape through the surface of the membrane, and any air movement is coming through the surface of the membrane rather than through any air gaps. At the time of testing, condensation was visible in the ventilated roof, where none was apparent on the underside of the roof shield under the same conditions. In close-up, the quantity of condensation present suggests the ventilated roof is not performing optimally. The results of the testing are shown here, and it can be seen that the non-ventilated air-permeable roof shield roof has air change rates comparable to conventional ventilated roofing. The conclusion of this testing is that roof shield provides much more uniform ventilation through the roof space, rather than simply relying on passive-driven cross-ventilation via low-level eaves vents, high-ridge vents, or roof tile vents, allowing the water vapour to leave the roof space through the membrane without requiring the vapour to be carried in moving air. Which is really just a long-winded way of saying no vents, no VCLs, no problems. This confirms previous testing which has concluded repeatedly that non-ventilated roofs with air-permeable underlays perform at least as well and more often better than conventionally ventilated roofs, and do not suffer from condensation problems associated with LR underlays used without ventilation. The final testing topic we'll consider is nail sealing against water ingress. There has always been a concern that when using breathable fabrics that water may track into the roof through the holes made by fixings, particularly if the membrane is not draped to provide a runoff channel. To put this concern to test, nail sealability testing has been conducted on the roof shield membrane. In this test, a sample of roof shield membrane is mounted into a test frame, the upper chamber of which can be filled with water to introduce the hydrostatic head. The test sample is perforated with nails to simulate, for example, counterbatten fixings being made through the membrane. Once the nails are in place, the upper chamber is filled with water and the rate of water ingress or not into the lower chamber is assessed. In this case, no water is able to penetrate through the fixings into the lower chamber. Seen in the cross-section under a microscope, we can see how this sealing process works. The nail does not make a physical hole through the membrane, but rather separates the microscopic fibres around the fixing. These fibres then clench tight around the shank of the nail, forming an effective seal around the fixing, provided the nail remains in place. Many thanks for your time this afternoon, and just a quick reminder that we have a full product information, performance specification and BIM object downloads available online at www.proctorgroup.com. We'll now move on to the question and answer session.
Thanks, John. We'll now move on to the question and answer session. My name's Pamela Howat and I'm a technical researcher here at the Proctor Group. With me is our technical director Iain Fairnington, and we've been reviewing some of the questions that you've sent through so far. Comments are still open, so please feel free to add any additional questions as we go along. We've had a few questions in by emails already, so we'll start with this one if that's all right with you, Iain. Which additional technical guidance would you consider essential reading, and are there any conflicts in the advice these documents give?
Thanks, Pam. There is some technical guidance which has been covered in the webinar so far in terms of BS 5250, BS 5534 are all very good documents and good reference points. In terms of conflicts in the advice, there are some conflicts in terms of BBA certificates. Sometimes it doesn't replicate exactly what's in the BS 5250, but BS 5250 does say that third-party certification, where no ventilation is required, should be looked at. So it's not necessarily a conflict, it's more a addition to the standard, the additional reading. NHBC, again, is another document which is well worth considering, because it will say that you need to ventilate even if you're using a vapour permeable underlay. However, with an air permeable and vapour permeable membrane, you do not need to ventilate that as per the NHBC standards.
Great, thanks for that, Iain. Wondering if you had any thoughts on the uptake of vapour permeable underlays in the mass market, and whether in 2018 we can consider non-ventilation to be mainstream roofing practice.
Yeah, another good question. I think we are seeing the uptake of more vapour permeable underlays being used in the market, and I think people are seeing the benefits of using these membranes over traditional HR underlays and the reduction of ventilation and indeed the risk of condensation. So it is encouraging to see the market moving that way. As the market moves, I think the market is now within two camps: the vapour permeable underlay camp, along with ridge ventilation, which can be a solution that can be successful, or indeed the air permeable underlay without any ventilation, which, as the seminar has shown, has proven itself over a number of years now as a good solution and almost a fail-safe option, with less restrictions on the workmanship.
Thanks for that. Okay, let's take one of the questions that's come in from the YouTube channel. We've got Ryan McElroy there. He's asking a two-part question. He's asking about the warranty on the roof shield membrane and comment on how to determine the drape required where no counterbatten is required. Okay,
good question, Ryan. In terms of the warranty of the roof shield membrane, we do have a warranty through a third party where we can offer a 15-year warranty, but our BBA certificate does give specifiers peace of mind in terms of the product being fit for purpose and being fit for the life of the building.
And I think it's also worthwhile saying Roof Shield has been on the market now for over 21 years, so it's got really good long-term pedigree.
Indeed.
And on the drape side of things, Iain?
Yep, on the drape. There's been a lot of debate recently in a number of British standards that I sit on about the drape. The old standard used to say nominal 10mm drape, and that caused a lot of confusion and a lot of heartache. Indeed, with some roofs being re-roofed because it was deemed that the drape wasn't adequate. Really what we're looking for there is a drape that will give adequate drainage of any water falling on the underlay as the secondary protection and being able to drain to the gutter. So essentially, in the real world, if you could test with a bottle of water from the top of the ridge and let the water run and it runs to the gutter, then the drape is adequate. However, that's difficult to do in every roof, or indeed to put in any legislation. So what we're looking for is a drape. The new British Standard 5534 now gives a maximum drape, because if there is too much drape, then there could be an effect on the wind uplift in terms of the deflection of the underlay as the wind passes over the roof. So it's a maximum 15mm drape, rather than call on the 10mm drape where you had potentially overzealous building control inspectors climbing on roofs with tape measures, etc.
Okay, that leads quite nicely on to this question that came in by email, Iain. Have we ever seen a roof covering failure due to wind uplift ballooning the underlay? It seems that this would be more likely in Scotland, with us being that bit windier here.
Okay. Yep, again, that's another discussion point that has created quite a lot of controversy in the market and in terms of British standards. Have I ever seen the roof covering failure due to wind ballooning? No, I haven't. And indeed, I've spoken to a lot of roofers that haven't seen that either. However, some of my British Standard colleagues have shown photographs of it happening before, but personally I haven't seen it, and I haven't seen anybody that, or spoken to anybody that's had this issue. What we're designing for here is a 1 in 50 storm. Not quite sure when the last storm was, but it is a 1 in 50 storm where there is extreme wind, and really what the standard is doing is it's best to reduce any risks on the roof and the specifiers and the contractors to ensure the roof is adequately designed for that 1 in 50 storm, if and when it comes.
Thanks for that, Iain. Okay, let's go to one of the other ones from the live feed. Tom Fisher's asked, I'm converting my loft, turning a cold roof into a warm, livable space. I'm not experiencing condensation issues now, so do I need to replace the underlay? And if I did replace the underlay and use roof shield, will he need a VCL?
Tom, I think the question there would be what type of underlay is it that you've got at the moment. If it's a vapour permeable underlay, then there's less risk of you or less requirement for you to ventilate that roof. However, you might need to ventilate at the ridge. If it was an HR underlay, like a Type 1F felt, for example, then you would need to ventilate that roof, and you should create at least a 50mm air gap at the coombe in the ceiling. In terms of using a VCL, that really depends on whether you replace with roof shield or an air permeable underlay. If you used an air permeable underlay and the insulation was of closed cell, so a rigid board, then there's less requirement for you to use a vapour control there. If you're using an air permeable insulation, such as a mineral fibre, then a vapour control layer would be a better specification, especially if you're using an HR underlay or a vapour permeable airtight underlay.
Okay, thank you for that. We've had another question in through the channel. Robinson, has asked, when using a traditional sarking board as opposed to non-permeable OSB style boarding, do you require a typical 2 to 3mm gap between each of the sarking boards?
Yeah, this is another good question that we get quite a lot within the technical desk, obviously more in Scotland, where they are using sarking boards. The British Standard refers to sarking boards as being softwood sarking boards, which are softwood 150mm planks nominally, and they're butted together when they're constructed. Usually these boards have a higher moisture content because they're stored outside. Once covered with an underlay that is vapour permeable, this tends to leave the shrinkage in the boards, which provides 1 to 2mm air gaps between the boards. When we look at non-permeable boarding, we call that sheet sarking, and that sheet sarking could be OSB, could be chipboard, and therefore it's less breathable, bigger sheets, more glue, and therefore with a non-permeable OSB, we would advise that you ventilate that roof, because it doesn't matter how good the vapour permeable membrane on top is, because it's going to be restricted and dominated by the permeability of the sheet sarking.
Okay, there's some questions come in referring back to the PII testing that was referenced in the presentation. One question that was asked was there any real-world testing conducted alongside the PII test cells? Did that concur with the extreme test results?
Yeah, there was a number of tests done where projects were picked where there was some with ventilation and HR underlays were monitored, which showed the potential reservations or guidance that you have to take with an HR ventilated roof, and some of the problems that can happen with what has been a successful application. There was some vapour permeable underlays tested with no ventilation, which did experience higher moisture contents, and subsequently some of those underlays were tested for their vapour permeability, which didn't concur with what was claimed. Roof shield itself was tested in a roof which was actually the highest occupancy of any of the buildings, and was indeed the driest of any of the buildings, which further proved the concept of a low vapour permeability and high air permeability, which RoofShield has, improved the system, even in extreme cases with high occupancy.
Okay, last chance to get any questions in, because if not, this is our last question. Again, on the PII project, that was a while ago now. Has any further testing been undertaken since?
Yeah, Pam, you've asked me that question, and you'll be well aware of all the testing that we do.
Absolutely.
As technical researcher, RoofShield does take a big part of our work. So we're continually doing testing, improving the system with RoofShield. We have done some testing which the webinar did touch on, which was air tightness testing in a real life roof, to test how air permeable that loft was. That was some interesting work, and there's probably more work required on that, I'm sorry to tell you, Pam. But it was a really interesting bit of work to see exactly how that roof performed to a ventilated roof. And probably the most important thing was the consistent airflow that you get with an air permeable membrane, which you still get the same airflow with a ventilated roof, but it's obviously going to be sporadic where the ventilation is.
Well, good to know I'm still going to be kept busy over the time. Well, that seems to bring us to the end of all the questions that we've had sent in to us. Many thanks to all of you for attending this afternoon and submitting your questions. Today's presentation and this Q&A will be available on the Proctor Group YouTube channel and also available at our website www.proctorgroup.com. And all of you who've registered will be emailed links to that shortly, along with the transcripts from today's seminar. You can also download full product information, performance specifications and BIM objects for our full range of vapour permeable membranes at our website www.proctorgroup.com, and catch up with all our past webinars there, which are contained in our Learning Hub. Thank you.